Hello, fellow knowledge seekers. Ernis here, ready to embark on another illuminating journey through the world of cutting-edge research. Today, we're diving headfirst into a fascinating paper titled Multi-Infrastructure Camera Bird's Eye View Transformer with Relation-Aware Fusion for 3D Object Detection. Yeah, that's a mouthful, I know. But trust me, the insights are worth it. Now, picture this. You're standing at a bustling intersection, not as a pedestrian or driver, but as a silent observer perched high above, like a benevolent, all-seeing owl. You see cars zipping by, cyclists weaving through traffic, and pedestrians navigating crosswalks. But instead of using your own eyes, you're relying on a network of cameras strategically placed around the intersection. That's the essence of infrastructure-based perception, and it's what this paper is all about. The core idea? To build a system that can understand this complex scene using multiple cameras, even when those cameras have different viewpoints, varying degrees of image quality, or are partially obstructed. Think of it as assembling a jigsaw puzzle where some pieces are missing, and others are warped. Challenging, right? So, how do we tackle this? The authors introduce MIC, which stands for Multi-Infrastructure Camera Bird's Eye View Transformer. Let's break that down into digestible bits. Imagine we're building a cosmic city of understanding, and each key concept is a building within it. First stop. Bird's eye view, or BEV. Instead of processing images directly from each camera's perspective, the system transforms them into a top-down, bird's eye view of the scene. It's like flattening the 3D world onto a 2D map, making it easier to reason about the positions and movements of objects. Think of it as creating a universal canvas where all the cameras can paint their observations. Next, we have the transformer. No, not the robots in disguise, Morty. This is a powerful deep learning architecture that excels at handling complex relationships between different pieces of information. In this case, it's used to fuse the data from multiple cameras into a coherent representation of the scene. Now, here's where things get really interesting. Relation-aware fusion. You might be wondering, how does the system know which cameras to trust and how to combine their information? That's where the relation-aware part comes in. The authors use a clever trick. They model the geometric relationships between each camera and the BEV grid using a graph neural network, or GNN. Picture a network of interconnected nodes, where each node represents a camera or location in the BEV space. The connections between these nodes encode information about the distance, angle, and relative position between them. This GNN allows the system to learn which cameras have the best view of each part of the scene and to weight their contributions accordingly. It's like having a team of art critics who each have their own perspective on a painting, and the system learns to combine their opinions to get the most accurate assessment. Okay, so we've got our bird's eye view, our transformer, and our relation-aware fusion. But there's one more piece of the puzzle: robustness. What happens when a camera malfunctions, gets blocked by a tree, or is obscured by heavy rain? To address this, the authors introduce a clever training technique. They randomly mask out or degrade the images from some of the cameras during training. This forces the system to learn to rely on the remaining cameras and to become more resilient to sensor failures. It's like training a musician to play even when some of the strings on their instrument are broken. Now, to test their system, the authors created a massive new dataset called M2I, which stands for Multi-Camera, Multi-Layout Infrastructure Dataset. This dataset contains a staggering amount of data, frames, images, and million annotated bounding boxes. It features a wide variety of road layouts, camera configurations, and weather conditions. But that's not all. They also tested their system on a real-world dataset called raw scenes, which consists of footage from 8 cameras overlooking a highway in Germany. The results? MIC achieved state-of-the-art performance on both datasets, outperforming existing methods by a significant margin. The system was able to accurately detect cars, trucks, cyclists, and pedestrians, even in challenging conditions. And it was able to do so while maintaining robustness to sensor failures and varying camera viewpoints. So, what does all this mean? Well, it suggests that MIC is a promising approach to building robust and reliable infrastructure-based perception systems. These systems could be used to improve traffic flow, enhance safety, and enable new forms of cooperative autonomy. Imagine a future where our cities are seamlessly connected and intelligently managed by a network of smart cameras. it's a future that's closer than you might think. And that, my friends, concludes our journey into the world of MIC. I hope you found it as enlightening and inspiring as I did. Until next time, keep exploring, keep questioning, and keep pushing the boundaries of human knowledge.